Hello, today I'm going to talk about mass spectrometers. This is a super important video, and so you're going to want to take notes on this, and you're going to want to study it till you know it backwards, because tons of AP problems have some part of these ideas in them, because this device uses electric and magnetic field to separate isotopes of a material. So like you have carbon-12 and carbon-14, both in your body. And carbon-14 is radioactive. So you might want to, well, they use it for radioactive dating. That's how you tell how old something is, something organic that has carbon in it. They use carbon-14 in medical tests. So they need to be able to isolate out the carbon-14 so they can use it in the medical test. So it's just a device that lets you take a sample of, say, carbon and pull out the carbon-14. So if you have two different isotopes of the same element, like carbon-12 and carbon-14, the difference in them is they have the same charge, but they have different masses because they have different numbers of neutrons. And that's in chemistry. So if you didn't have that, then you should have taken chemistry. Okay, let's move on. So I'm sorry I'm holding this sideways here, but maybe you have to turn your head if you're watching it on TV, but if you're watching it on your phone, you're okay. Okay, so there's four parts of a mass spectrometer machine. There's the ionization part, acceleration part, speed selector part, and mass isolator part. All right, sounds like a lot, but I'll go through it. Okay, so you start out with a bunch of like carbon-12 and carbon-14 together, and the first part of the machine charges all the isotopes up. So make sure all the particles are charged, okay? It does that by like rubbing them together or something. I don't really know how it does it, but that's not the important stage of the machine. The rest of it's what's important. The second part of the machine uses electric fields to speed the charged particles up. The third part of the machine, now the particles are all sped up. It only allows particles of an exact certain velocity to continue on straight. If they're going too slow or too fast, they'll curve up or down. You'll see why in a minute. And so when you get through region 3, we know exactly how fast they're going. All right, that's important because in the last part of the machine, it separates the particles by mass, isolating a certain isotope. Okay, here's the physics behind it. Okay, like I said, the first part doesn't really matter. Somehow they charge up the particles. So you got charged up particles and they shoot them in region 2. So if they're positively charged and you shoot them in region 2, region 2's goal is to speed up the particles. Now I made this kind of narrow because of my piece of paper, but it could really be further apart. So if you shoot a positive particle in and there's a negative plate over here, of course it's going to accelerate towards the negative plate. So you're using an electric field in region 2, and electric field lines are drawn from positive to negative. So electric field lines, envision them all drawn here. And the positively charged particles are going to speed up in region 2. All right. Now, the third region, which is right here, we want only a certain speed to go straight through. If they're going too fast or too slow, we want them to curve up or down. So the goal of region 3 is to know exactly how fast they're going when we get to the end of that region. And they do that with an electric and a magnetic field. So here's the electric field here, the positives and the negatives. So the electric field lines go from positive to negative, right? And the positive charge, when he comes in this region, he's going to want to curve down toward the negative plate because of he's a positive charge and this is negative, right? So there's going to be a force on him downward, the electric force. Well, you want an exact certain speed particle to go straight through. So you need a magnetic field such that the magnetic force on the particle is the same as the electric force. So the magnetic field in this case is directed into the page. So if we have a right-hand rule, the particle's going this way with a magnetic field going into the page, then he'll feel a push up, right? and that's the magnetic force. So the particle comes in here, he has an electric force down on him, and if he's going exactly the right speed, he'll have a magnetic force up on him that equals the electric force. Here's the math. So the electric force is QE, right? Force electric equals QE, and the magnetic force is QVB. So the charge cancels out, and his velocity is equal to the electric field divided by the magnetic field. So that's how you get an exact velocity that you want. If one of these is bigger than the other, then if the electric field is bigger, right, then he's going to swoop down. And if the magnetic field is too strong, he's going to swoop up. But if you have exactly the right magnetic and electric fields, he'll go straight through. All right, so he now has the electric and magnetic field. He goes straight through. Now we have the mass isolator part, and that is only a magnetic field. Now I've drawn the magnetic field here coming out of the page. So here he comes through here, boom, in a straight line. So if he's coming that way with the magnetic field coming out of the page, he's going to feel a push down, right? So he's going to come in here and go whoop and do a circle, boom. Now here's the deal. Force magnetic is QVB, and he's going in a circle, and that circular force is the centripetal force equals mv squared over r. So his mass, the radius that he travels in depends on his mass, because the charge is set by whatever you charge it in region 1. The magnetic field you've set, it's a constant, and the speed is a constant because all these particles coming into this region are going the same speed. So what happens is if you have a bigger mass particle that comes through here, like a bigger isotope, it'll be going a bigger radius. Whoop. So now all you have to have here is buckets. A bucket here and a bucket here. This bucket is going to collect all the less massive ones because the radius is smaller. And this bucket is going to collect the more massive ones because the radius is bigger. So now you've isolated them by bucket, and you take out the carbon 14, of course, is more massive, right? So this would be your carbon 14, and this would be your carbon 12. Isn't that cool? Very, very cool. Okay, I'll leave that there for you to look at for a second. And that math, you have to know all of this. You just have to do this over and over again until you're very, very comfortable with it. All right, I have two problems, two AP multiple choice problems that I want you to do. This is 1976 E3. Here's the, this is a version, so this doesn't have 4 regions. So this has a particle that has a mass of m, a velocity of v, a charge of q, going into region 1, has an E field pointing up and a magnetic field out of the page. And then it goes into region 2 that has a magnetic field out of the page but no electric field. And here are your questions. What is the force on the particle at P2? This is what this particle does. Is it positively or negatively, that's an N, positively or negatively charged? Explained by the direction it goes and everything. What is the speed and the velocity at P1 in terms of these? And what is the mass of the particle in terms of the magnetic field, the electric field, the charge, and the radius here? Okay, that was 1976 E3. Okay, I want you to do that one. The second one I want you to do is 1990 E2. There it is. And that's pretty easy to see. It has a region 1, region 2, and region 3. They don't really, let's see, that's a mass spectrometer. It's accelerated from rest in region 1. So see, they haven't even put the ionization part in. They just are starting with region 2 and calling it region 1. So no big deal. Anyhow, it goes through an electric field, a magnetic field, and an electric field, and then a magnetic field in region 3. Okay, so that's your work to do next time you're together is watch this video and do those 2 problems. And you can look up the answers yourself because I just told you what years they were. I have the answers to 1976. If you can't find them online, just email me and I'll send you a picture of them. All right, have fun. Mass Spec.